Let's begin this section on sound by reviewing some of the primary concepts. We found that there are many sources of sound, and sound travels outward. It radiates outward in a wave-like pattern. These waves are not like ocean waves, but rather they're compression-expansion waves, push and pull, and can be demonstrated using a slinky. There are certain characteristics that describe sound, like pitch, frequency, or intensity and loudness. The intensity is the amount of energy that's traveling in the wave, and the pitch is related to the frequency, which is the number of waves per second that pass a particular point, or cycles per second. The greater the frequency, the higher the pitch. We did some experiments and found that sound travels through solids, liquids, and gases. And we also found that the thin, smaller, shorter objects have a higher frequency. It vibrates faster than the long, large, more massive objects. We looked at the ear and how it operates and functions and transfers the vibrations and turns them into electrical impulses. And we investigated our larynx and saw how we can make noises by stretching our vocal cords. Besides pitch and intensity, there's a third characteristic that helps us to describe and classify sounds, and that is quality. Let's say that we have a violin and a banjo, and we're going to play a middle C on both instruments. How can we tell the difference between the violin and the banjo? The middle C is the same pitch on both, 256 cycles per second. And if we play them with the same intensity, that's the same also. How can we tell one from the other? Well, there's a thing called overtones. It's called a harmonic, and it means that the string is not only vibrating at its fundamental frequency, which is 256, but it's also vibrating at increments of that frequency. For example, it may be vibrating not only from one side to the other, but vibrating around the midpoint of the string. That would be a second harmonic, or 512 cycles per second. And then we could have a third harmonic, which would be 3 times the fundamental frequency, and in this case it would be 768 cycles per second. The final product, the noise that you hear from that string, is a combination of overtones or harmonics at different intensities. And a violin has a characteristic that makes certain overtones at certain intensities, and a banjo has different ones. As a result, when we hear a middle C on a banjo, we can tell we're listening to a banjo and not a violin. And even one violin to another has unique overtones, and an expensive violin will sound a lot better because it has cleaner overtones. Even if you haven't tried this yourself, you've probably seen someone who has. I'm referring to taking a breath of helium from a balloon and then talking, and you sound like Alvin the Chipmunk. Well, first we should discuss safety. Is it safe to breathe helium before we even try it? Remember that helium is on the right-hand side of the periodic table. It's one of those inert gases. It doesn't combine with any other element. And then if we do the research, we find that deep-sea divers breathe a combination of helium and oxygen because it's dangerous to breathe nitrogen and oxygen at deep depths because the nitrogen dissolves in the blood and the helium doesn't. So it's safe to breathe helium if you don't breathe it continuously because the body, of course, needs oxygen to live, and you'd black out if you breathe too much of it. Now, remember that helium is much lighter than air. It's much less dense. And if we know about sound, sound travels faster through helium than it does through air. In fact, it travels about 4 times faster. And remember, less dense materials produce higher frequencies. So when we talk, we would expect to hear our voice with a higher frequency. And listen, here's what it sounds like.
Isn't science fun? We always have fun with science.
Can you see yourself like this, walking to class with a garden hose slung over your shoulder? Well, it's a real useful item if you're going to be investigating the speed of sound. How fast does sound travel? In air, it travels at about 750 miles an hour. This translates to about 1,100 feet per second, or in the metric system, 340 meters per second. Let's just think of it as traveling rounded off to 1,000 feet per second. If it travels 1,000 feet in 1 second, It'll travel a mile, which is about 5,000 feet, in 5 seconds. Okay, let's go to this lightning thunder idea. We're outside in a lightning storm. We see the flash of lightning. The light hits our eyes almost immediately because light travels so very, very fast. And then we start counting seconds until we hear the thunder. Every 5 seconds will equal 1 mile away. The way I remember this 5-second rule is the number of fingers on a hand. We observe this effect in many different ways. At a baseball game, you see the batter hit the ball, and then later, some time later, you hear the crack of the ball hitting the bat. At a firework display, you see the exploding beautiful firework, and then a split second later you hear the big boom from the firework. Now, why the garden hose? Well, this garden hose is about 50 feet long, and we know that sound travels 1,000 feet in 1 second. So it'll travel 50 feet in 50 over 1,000th of a second. So that comes out to be about 1/20th of a second. And if I talk in one end and listen in the other end, I'll hear my own voice delayed by 1/20th of a second. Now there's another concept here too, the idea of why cheerleaders use megaphones at football games. The sound is being directed, all the sound is being directed down this tube and pushed through this tube. It's not allowed to expand outward like sound likes to do and dissipate around us. It's being focused in a tube, so it will travel much further. And it'll go around all these loops. It'll even go around corners as long as it's in a flexible tube and not pinched. And if you listen real well, you can hear your voice in this ear when you talk, and you can hear the delayed voice in the other ear when you put this to your ear. And it sounds like this. Don't forget to remove the water from the hose before you bring it to class. Vibration is a concept in sound that's easy to demonstrate. The frequency of the sound, or the number of vibrations per second, is measured in either cycles per second or hertz, and they mean the same thing, and hertz is abbreviated sometimes Hz. Now our ear can hear a low frequency sound down to about 20 cycles per second and up through the range to a high frequency of about 20,000. Beyond that is the ultrasonic region. Some animals can hear frequencies above, like a dog for example can hear 25,000 cycles per second. Let's look at some musical instruments. A piano, the low key on a piano is 27 hertz and the high key is about 4,000. And a violin can play a tone of about up to 10,000 cycles per second. There's some activities you can use to demonstrate vibration. This first one uses a paper towel tube, and I've cut a balloon in half and stretched it tightly over the end of the tube. I've also fashioned a cone that fits nice and tight over this end. As I make sounds on this diaphragm, the vibrations carry through the air and push a lot of air out the very tip of this little cone. And as we hold it near a candle flame, there's a certain tone of vibrational frequency that works best that I've discovered. But watch what it does to the flame. This one should be done as a demonstration because I've more than once caught the tip of this little cone on fire, and you have to be careful. Another really good one is to get your tape recorder and get the perfect music. There's the right kind of music with lots of percussion in it. And then get an orange juice can, cut the metal end out of it, and stretch a balloon, just like you did here, over the top of the can. Make it nice and tight. Set it on the speaker of the tape recorder, and then with a little paper collar, slide it over the top of the orange juice can so it makes like a little barrier, so you can put popcorn kernels in on the stretch balloon. This time we're going to turn on the tape recorder and play the music, and watch what happens here. Bet you didn't know popcorn could dance so well. This next activity can get every student involved. This time use small cardboard tubes, and once again cut balloons in half and stretch them tightly over the end of the tube and secure them with a rubber band if you need to. Cut some tiny little squares of mirror, about 1 centimeter square, and if you need instructions on doing this, look in the light section of the K3 physical science tape. They're easy to cut. We want to secure this mirror to the end of the balloon. One easy way to do it is to get a piece of tape, roll it on itself, stick it on the bottom of the mirror, and then onto the middle of the balloon. You've now made a little light amplifier. As we speak in here, we can bounce light off the mirror onto a dark wall and see the waves bounce along the wall. This works really great. Have your students go outside, face the sun so the light can hit the mirror and then bounce into a dark wall. Have them talk or make noises into the little tube. They'll see the image bouncing along on the wall. There's a certain tone they can make where they'll get a circular image. That means that the mirror is rotating around in a circle. The little diaphragm, the little stretched balloon, is vibrating at its fundamental frequency. It's making that one wave going up and then going down, and it'll make a little circular figure. It looks really exciting. Your students will really like this. If you can make enough, let them take them home to play with them. The final activity is one I'm sure we've all done, and that's making our own phonograph. And very easy to do. Just roll up a piece of paper into a cone shaped and then get a straight pin and run it through the end. I like to fold it in half and then run the pin through the end like you see here. Now be sure and use an old record because it's not good for the grooves to run a straight pin through it. The grooves make the needle vibrate. These vibrations travel up through the paper and make it vibrate. In turn, the air inside the cone vibrates and we can hear the sounds. Let's turn our record on and listen to the music. It's not really stereo hi-fi, but it does illustrate how vibrations travel. Speaking of travel, remember when we were young, we used to ride our bicycles with those pieces of cardboard and clothespins in the tires, and the faster we went, the more they vibrated and the higher frequency sound they made. That's another good activity to try. There's a couple more topics that you may want to branch out into. One is sound insulation, materials that absorb sound. And for example, I found egg cartons work really well. Another one is the way we use two ears to triangulate on sound, and if we covered one ear, it would be more difficult to locate the source of the sound. Finally, as we cover through all these sections on sound, it's important to talk about the safety and proper protection of our sense of hearing.